Alright guys, here's a problem from chapter 16 that involves a piston, a frictionless piston. In this case we're going to have a piston that we imagine being on top of this cylinder, and we drop it down and it oscillates and then eventually comes to rest at a final height h1. And we're going to try and calculate what that height h1 is in terms of the initial height h0. So we have two states in this problem. We have the one where the piston is out of the tube, and we have the one where the piston is in its final state. So initially, we have that the pressure P1 is going to be just atmospheric pressure. When the piston is outside of the cylinder here, the pressure in the gas is just going to be, or the pressure in the cylinder is just going to be atmospheric pressure because it's in equilibrium with the atmosphere. So our pressure at state 1 is just going to be equal to atmospheric pressure. And the initial volume, V1, is going to be equal to H0, which is the total height of the cylinder, times the area of the cylinder, A. So this is going to be H0 times A. Okay, and then we drop the piston in, and this is the final state that the piston arrives at. So we can say at rest, after we've dropped it, we're going to have then P2 is going to be what's labeled P gas here on the figure. We don't know what that pressure is going to be, but we are going to have some pressure of the gas after the cylinder, after the piston comes to rest in the cylinder. And in order to calculate that, we need to realize that this piston here is in mechanical equilibrium. We've got some down forces acting on it, and the gas is exerting an upward force, and when the piston is at rest here, the downward forces are equal to the upward forces. So let's go ahead and do a free body diagram since the piston is in mechanical equilibrium here. And for an upward force, we just have the force of the gas up on piston. The pressure here is exerting an upward force on the piston, and downward we have atmospheric pressure, the force of the atmosphere, in addition to the force of gravity due to the mass of the piston. Alright, so if we sum the forces in the y direction, we're going to get our up force, which is the force from the gas, minus the force of the atmosphere, minus the force of gravity. It's going to be equal to the mass times the acceleration in the y direction, and since it's at rest, we'll take that to be 0. Alright, so what we're interested in is an expression for the pressure for the gas. So let's convert these forces to pressure, and so we can rewrite the force of the gas as the pressure of the gas times the area of the cylinder, and minus atmospheric pressure times the area of the cylinder. Then we have the force of the gas, or excuse me, the force of gravity, which is just going to be the mass of the cylinder times g, and that's all going to be equal to 0. So now we can solve for the pressure of the gas. It's going to be equal to atmospheric pressure plus mg divided by A. Alright, so now we've done the steps of with the piston in terms of Newton's laws of mechanical equilibrium. Let's go ahead and apply the ideal gas law. So in the initial state, we're going to have P1 V1 is equal to nRT1. And actually, I'm not just going to write nRT because we're going to assume that the piston falls slowly enough that any increase in temperature in the gas can flow out of the cylinder into the environment. And so this remains isothermal, meaning it's at the same temperature the entire time. So we're just going to use one variable t with no subscript for both the initial and final state. And we have an expression for P1 and for V1, so we can rewrite this. I'm going to go ahead and rewrite it down here as being equal to atmospheric pressure times H0 times A. That's P1 times V1. And on the right-hand side, we're going to have nRT. Now in the final state, we're going to have some P2 times V2 is equal to nRT2. And we've already said that the pressure in state 2 is equal to the gas pressure here that's labeled P gas. And we've solved using Newton's laws for an expression for P gas. So let's go ahead and plug that in for P2. That's going to be atmospheric pressure plus m times g divided by A. That's P2 times V2, which is going to be our height h1 times the cross-sectional area A. So this is going to be h1 times A. And that is equal to nRT. And once again, I'm dropping the subscript because this is an isothermal process. So now we can set these two equations equal to one another. We get atmospheric pressure times H0 times A is equal to atmospheric pressure plus mg divided by A times H1 times A. Our A's on the outside are going to cancel. We get that H1 is equal to atmospheric pressure divided by atmospheric pressure plus m times g divided by A, all times the initial height, h0. All right, so if we plug in some conventional values here, assuming the mass of the cylinder, or excuse me, the mass of the piston is 2 kilograms, maybe the area of the cylinder is 4 centimeters, and taking atmospheric pressure to be 1 atmosphere, we find that the final height, h1, is about 87% of the original height, h0. All right, guys, so there's another example problem from chapter 16.